Hello and welcome all of you. We are going to be looking at solids of revolution today. So projected solids are a different kind of solid than this is. Projected solids, or solids of known cross-section, are exactly that. It's when the cross-section of the shape is a particular shape, like a semicircle or a square, and those squares or semicircles could vary in size, but they all are the same sort of slice. Solids of revolution are, as the name suggests, created by revolving something. And so here's my little math teacher joke. If you took France and revolved it, you'd get the French Revolution. Anyway, but that's what we're doing here is we're taking a flat shape and revolving it to get a solid. And we're going to be in need of thinking about how do I get cross sections that are similar in shape from such a process. Okay, so note that this online lesson is going to just cover certain cases. We're going to deal with a couple other cases in class, but they all come down to the same bare bones if you just keep that in mind. Okay, as a warm-up today, I have a couple of pictures, and these were stolen from your old geometry book. So I know you know how to do this because you passed geometry. So I would like you to find the volume of each of these shapes and leave your answer in terms of pi. Please pause the video to do so. Your answer should be as given here in terms of pi. And the work for these is over here. Let me move this out of your way. Are these two calculations. So for the first one, you find the volume of a cone, 1/3 radius squared times height. Volume of a cylinder is area at the base times the height. So pi r squared times height. And then just add those together. For the other one, it's a subtraction issue. So you would find the volume of the large cylinder and subtract the volume of the small cylinder. Now those answers, as it turns out, could be found this way with geometry, but also could be found with calculus because both of these are what we would call a solid of revolution. If I were to take this triangle and revolve it around this line, and think of that triangle as if it left a path behind it, okay? So just like when I take this point and move it and leave a trail behind it, I'm drawing an arc, okay, or a function of some kind. If I were taking this triangle and having it leave a path behind itself, as I revolved, I would generate this cone. To generate the cylinder, I would be taking a flat shape like this rectangle and be revolving that around the same axis of revolution, if you will. And then that would obviously be the way that I would make either of these other two cylinders, right? I would be revolving a big rectangle for the large cylinder, right? This big rectangle. And then the hole, or the empty space, would be revolving this smaller rectangle. And I'm subtracting off the hole, okay? And don't get confused when I say hole out loud. Sometimes it's confusing. I'm subtracting the hole, not the hole, okay? Don't get confused. All right, so subtracting that empty space, right, would leave me with the part that is actually solid. So both of these are actually solids of revolution. So we can determine their volumes not only with geometry, but with calculus. Something I've seen in day-to-day life that is a solid of revolution and does exactly what I was saying a second ago about leaving a path is this kind of party decoration. So if you've ever seen these, they start out as a flat shape like you can see in this package here, and then you open them up and they leave this honeycomb shape behind them, and they are solids of revolution. So I just thought I'd mention that. Okay, so let's say that we wanted to be fancy and determine the volume without calculus. Now, given what we know about solids, about projected solids, we'd like our slices to be the same shape all the time. And that is going to be hard to do, or easy to do in one direction. Let me say it that way, say it in the positive. So it's really easy if we go this way. All of these slices would be various sized circles. And it might be surprising to you that they would be circles, but if you think about the fact that we had our axis of revolution and that a bunch of different points all revolved around that axis, it shouldn't be super surprising that you'd get a circle, right? Isn't that what you'd get when you take a point and revolve it around a line? So we have all these different points along this edge, so to speak, okay? And they all are being revolved around this other line, and that's going to make circles, okay? Now these circles we typically call discs. That's the traditional name. I had a class recently that wanted to call them all pancakes. I respect that. I love the pancake. A stack of pancakes here, I mean, that's a great visual. I'm just picturing syrup now, okay? So the fact of there being slices should suggest to you integration, right? Because when we had a two-dimensional situation and we wanted to find area of a flat shape, we sliced it up. And as those slices got infinitesimally smaller, those rectangles that we were making got more and more and more accurate, and that gave us the exact area. So if we understand that integration is when I add together infinitesimals, then adding together these infinitely thin pancakes is very much what I would like to do, okay? So we are going to have to, in order to do calculus here, put this on a coordinate plane. That's sort of the issue. So let's just say, we could do this in any number of ways, but let's just say that this is the origin, okay? And then this point up here is 12 units higher along that red line, so that would be 0, 12. And this point over here, because the radius is given to be 9, this point would be 9, 0. So what that would tell me with a little bit of effort here is that this guy is the line y equals, let's see, it would be a slope of negative 4/3 x and a y-intercept of 12. Okay, so that's what I am looking at. And because I'm revolving in the manner that I am, okay, my axis is vertical. This is not really going to be what our focus is today, but I happen to be doing this one problem this way. If your axis is vertical and you're revolving, think about where your radius is. Your radius is going horizontally. And if I want to know a horizontal distance, I need to do the right endpoint minus the left endpoint. So I understand that my left edge is at 0, but my right edge is going to be determined by this line, but not as a function of x, but rather as a function of y. So if I reorganize this, I would have, let's see, I would subtract the 12, so I'd have x equals y minus 12, and then I'd have to multiply by the reciprocal. Okay, so there's a couple algebra steps that I did there all together. Feel free to write more if you need to, okay, like work that out for yourself, okay? Now, since each slice is a circle, my volume is going to be found by integrating the area. And area in this case is pi r squared, and it's going to be in terms of y, okay, because I'm revolving in this manner, right, around this vertical axis. So I'm going to have pi, and then each radius, all of these radii are different as you go through different parts of the cone, right? But they're all different based on where they are on this y-axis. Okay, so the y coordinate is determining that. And so I'm going to put my equation, this one, into my integral. Okay, and that's determining the radius. So that's the radius squared in terms of y. And since I have dy, since I've identified y as my independent variable, my bounds have to be in terms of y as well. So going from 0 to 12. So that would be just doing the cone. I could do the cylinder in a similar manner, and I would get this answer from before. So you could even check yourself, try that and see if you can manage it. But my point in showing this is not so much doing this particular problem, but just really showing you that the volume specific to this method, and by this method I mean disks for a solid of revolution, is volume is a definite integral, so you'd have to have bounds, of pi r squared d whatever. Okay, could be dx, could be dy, because in general, as you already know, if I integrate area, I get volume. And that can be in terms of either variable, because integrating cross-sectional area gives us volume. Okay, so what we're going to focus on in the next few examples are dx setups. This is the more commonly asked about one, fortunately for us, but I just wanted to try to break it down into a couple subcases. Okay, so the first case that we're really going to focus on beyond that, introductory example is just looking at dx. Okay, we're going to do this one together. So it says determine the volume of a solid obtained by rotating the region bounded by, okay, that's going to be some parabola. So I'm going to draw in my little parabola here. It has to have a y-intercept at 5, so this must be 0, 5. Okay, so some kind of parabola upward facing, x equals 4 is a vertical line. X equals 1 is a different vertical line, and the x-axis. Okay, so now notice the English. It was describing the region. The region is bounded by, and now as it lists these things, boom, 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 those are the boundaries. And then we're going to take that region and rotate it around the x-axis. Sometimes people struggle with the English on this. You just have to read very precisely. Okay, so the region we're talking about is this region enclosed by those boundaries. And I'm going to revolve that around the x-axis. And you will see in different sources, including in your book, that they sometimes will draw like a little arrow like that just to remind themselves of which way they're going. Okay, now this is true confession time. I'm a terrible drawer. In case you didn't already know that, you probably did. But what I like to do in terms of trying to get myself a picture is I first just try to draw a reflection image. So I reflect across the axis of revolution. And then I try to make this look three-dimensional by adding some of those disks. So that point, for example, would rotate to here, and then it would come back behind the shape. This point would rotate to here and would come back around. And I maybe see that side because of, being on the end. And then I can do some more little disks like that in between to try to show the 3D-ness of this. Okay, now fortunately for all of us who are not great drawers, the drawing part is really important initially because you're going to need to conceive of like what it is you're talking about. But as you do more of these, you can do a lot of them just with a two-dimensional drawing and just like in your head thinking about the 3D shape, okay? But thank you for suffering along with my poor drawing skills, okay? It especially does not translate well when you can't shade. You might find that you have better pictures when you're using a pencil because you can do some shading. All right, so here is my shape, and it looks like some kind of weird vase on its side or something like that. So I know that my slices are going this direction, which means my radii are these kind of segments. Okay, and if I need to find a vertical, I'm going to go from top to bottom. And so I can just take this function as it stands. Okay, so my integral is going to be a dx integral. I'm going to have pi r squared dx. And my radius is going from this purple curve down to the bottom. And the purple curve was this equation. So x squared minus 4x plus 5 minus 0, technically. Okay, but I didn't write that. And then my bounds, because I have dx, would be my x goes from blank to blank. So x here starts at 1 and it goes up to 4. Okay, now the focus of this really is going to be on setting up the integral, because at this point you could throw that into your calculator using fnint. Fine, that's really not the point, though I understand that sometimes you're going to want an answer so you can check your setup. Okay, so this is the numerical answer, but that is not going to be the focus of this video. The focus is going to be, can you think of the shape and can you set up the integral? Okay. Our next one, your printed notes, I believe, still have a typo that I've been carrying for a couple of years now, because I just never get back to fixing it. So please cross out the part that I have crossed out. And I also would like to emphasize we are only talking about the region in quadrant 1. Okay, so find the volume of the solid by rotating the region in quadrant 1, defined by the intersections of those shapes. Well, let's work on the shapes together, and then I'm going to have you try the rest yourself. Okay, so this is a downward facing parabola. This tells me that this point is 0, 4. I am only looking at the part in quadrant 1. My other boundaries, these two, are the axes. So the region of which we are speaking is this part in here. Okay, so that little nubbin. Now, if it's confusing to you to have extra pieces around, you certainly can just take away these extra like bits and understand that you are just revolving that little nubbin, and the way that you're revolving it is around the x-axis. Okay, so it's going to make a shape that looks kind of like a dome. Okay, all right, I'd like you to set it up, pause the video to do so, and then come back and check your work. All right, here is our setup. So my work actually would begin down here because I know that I need to find this point, and that's an x-intercept. So x-intercepts are found by letting y equal 0. So that place where the parabola hits the x-axis is at +2, and that means my bounds are from 0 to 2. The slices we'd be talking about, I didn't even draw in the shape, but the slices that we would be talking about are all going this way. So here's an example of a representative disk or pancake. Okay, and then here would be a radius. So the radius would run from the blue curve down to 0. So here's my blue curve equation. I could also have written -0, and I'm using pi r squared as my structure because each slice is a circle. In my next example, I have the standard parabola y equals x squared. I have a downward sloping line that goes through 12 and on the y-axis and 3 on the x-axis. Notice I have an edit on the wording of this as given. And it says find the volume of the solid determined by rotating the region defined by, okay, so now here are all my boundaries. The blue curve, the black line, y equals 0. Y equals 0 is this. So the part that we're talking about is this little pocket right in here. Okay, it's always going to be an enclosed space, right? You can't just have like an open end because what do we do with that? Okay, so it's this little triangular-esque shape, okay, that's being revolved. And again, you can erase the extra pieces if that is confusing to you. But I'm going to draw my reflection, or try to draw a reflection. That wasn't very good. Draw a reflection image and then try to make it look 3D. Okay, so something that's more like a prickle here. Okay, and so it's like this. It looks kind of like a top, right? Well, I went dotted there. Okay, and then here, right, like a kid's top, like a toy. All right, so that's our picture. And I can see that something interesting happens in this one. In particular, this radius goes from the blue down to 0, but a radius over here would be going from the black function down to 0, which means there has to be a place where that changes. And indeed, right here is where the change occurs, okay? So this point, if you just figure out where these two lines cross, is at 2, 4. That is an algebra skill, right? Just like finding any time when two things cross, right, you set them equal to each other. Solve that through factoring. Okay, hopefully that's not the mysterious part of the question. Okay, so we solve that and we get that x is 2 is one of our solutions. You can take that answer of 2 and plug it into either of these equations and find that the other coordinate is 4. Okay, so 2, 4. And then this point, clearly from observation, it's just the origin. Okay, so the way that we're going to set this up is going to be in 2 pieces, kind of like what we did with certain area problems where the edge changes. So here, from 0 to 2, we're going to have pi r squared, and then as well, from 2 to 3, we're going to have pi r squared, but our radius is going to change. From 0 to 2, our radius is the x squared function, and this time I am going to write the minus 0, just for clarity, right? This is the top, this is the bottom. That is how you find vertical distance. This purple line, I'm going from the parabola down to the x-axis. And then for the other part, the part from 2 to 3, that's that black line. And so from 2 to 3, I have my black line, and I could write minus 0 if I wanted. And that black line equation is determining my radius. All right, so those are our dx examples for now. And I wish you well. There are more videos related to this topic.